Hello everyone, welcome to Headway Civil Online Study. In this video, we will learn about the grain size distribution. The grain size analysis is widely used in the classification of soil. The data that are obtained from grain size distribution curves are used in the design of filters for earthen dams and to determine suitability of soil for road constructions. So, what do you mean by grain size distribution? In this case, the determination of the mass of materials in fractions containing only particles of certain sizes is termed as mechanical analysis. Right, so the mechanical analysis can be grouped or can be divided into two parts. The first one is the sieve analysis and the second is the weight mechanical analysis. In sieve analysis, generally we do for coarse grained soil having particle size greater than 75 micron. Okay, so this is basically done for coarse grained soil for size of particle greater than 75 micron, and this is generally done for fine grained soil having size of particle lesser than 75 micron. Remember, 1 micron is equivalent to 0.001 mm. Okay, so the values you always need to represent it in terms of mm while doing the plotting the curve. So this relationship is required, right? So in this video we will learn about the grain size distribution, how to do using the sieve analysis. So the sieve analysis is carried out how? By sieving a known dry mass of sample through the set of sieves placed one below the other so that the openings decreases in size from the top sieve downwards. This is how the placing takes place. If we consider set of sieves that are chosen, sieves are somehow arranged like this, and at the bottom there will be a pan that is being contained, right? So the topmost sieve will be coarser one. That means it will have the size of opening larger and it will be the finer one. Okay, so the size of opening of this sieve will be smaller, so that when we put about say x gram of soil mass into this dry soil mass, remember, so that the and subject this to mechanical shaking. This entire arrangement is subjected to mechanical shaking for about some time, maybe 10 minutes of, or it basically depends upon the type of soil we are subjecting it to, right? Next, what will happen? The certain amount of particles which get retained on each of the sieve, right? So few particles will get retained on each of the sieve. So we'll weigh this mass as say M1, M2, M3, M4 and M5, right? So this will be M1, this will be M2, say M3 and M4 and M5. So this is how we weigh this mass. Okay, next, after calculating this mass that is retained on each of these sieve, we need to find out what is the percentage of mass retained on each sieve. How to find out the percentage of mass retained on each sieve? See, here it's a percentage of mass. It's showing the retained on each sieve. This will be, say in the first sieve M1 is retained, so we'll write M1 divided by this total mass is X, so we'll write M1 divided by X into 100. So for M2 it will be M2 by X into 100, M3 will be M3 by X into 100. So I'll show you in the tabulated format and with an example in the in this video itself. At the end of this video I'll show you. Okay, next what we need to do is we need to calculate the percentage retained on each sieve. So what do you mean by cumulative percentage retained on each sieve? It is the total percentage amount of soil which could not pass a particular sieve. So that percentage amount of soil will have grain size greater than that sieve number. Okay, see, if we consider this particular sieve, this sieve, okay, this sieve we are considering, that means cumulative percentage means it is the total percentage amount of soil which could not pass through this particular sieve. Say this is the sieve number 3 which could not pass this number 3 sieve. Okay, so how to calculate this? I'll be showing you. It will come out with the sum of percentage retained on all courses sieves. Okay. After calculating the cumulative percentage, we need to find out the percentage final, which will be 100 minus cumulative percentage retained. Once we are completing with all these calculation, that is percentage retained, cumulative percentage retained and percentage final, what we need to do is we need to plot a graph in a semi-log graph paper and will obtain a curve using these data. So how it will be? Let us see. So we will be plotting a graph. The graph will look somehow like this, where this will be the log scale, since I already told it's a semi-log graph paper, and here it will be the arithmetic scale. Okay, this scale will be arithmetic scale, that is the normal scale in the normal graph paper that we see. Okay, so this let be the values. Here we will be plotting the percentage final, that is the data we are obtaining from this value after subtracting 100 minus the cumulative percentage retained. And in the log scale, we'll be plotting the size of grains, or we can say it's similar to that of the, or we can say sieve size. Both are similar. Okay, this will be in mm. So we will obtain certain curves somehow like this, say this, or somehow like this, or somehow some graphs somehow like this. So seeing at the curve that we obtained, how to classify whether the soil is well graded or poorly graded or uniformly graded or gap graded. Now let us look at this. Okay, so here is a graph that is plotted between the sieve size and the percent final, and you can see there are a lot of curves that is being drawn. We will get concerned about few of the terms. Okay, now let us look at the first. Let us look at this dotted line that we have. This is the dotted line we have. You can see over here, this is the dotted line that's it's growing. Okay, so we can see that this dotted line is covering all size of particles. We know the finest particle is the clay, and as we move from here to this side, the coarser particles we are approaching towards, right? So clay is the finest one, then is the silt, sand and gravels. As you can see over here, is the clay is the finer. Next we have got silt. As we increase the sizes, then we'll have gravels, sand, gravels, and then cobble. Okay, so as we can see from this curve, it is the dotted line is covering the entire region. That means the curve is passing through all the zones: clay, silt, sand and gravels. So we can classify such soil as well graded soil. So this will be considered as well graded soil. Seeing at the curve itself, that means well graded soil will comprise of particle size all throughout of different particle sizes. Okay, now if we consider this graph, say somehow this graph we are considering, that means this curve is passing only through the sand zone itself. There is no clay, silts or gravels. Since we can consider such soil as uniformly graded soil, or we can say is poorly graded. So what do we mean by uniformly graded? That means it is comprising of particle sizes of only a particular zone. That means it has got only sand particle size. It doesn't comprise of clay, silt or gravels. There is another group of soil, or we can say the curve that we can draw, or we can obtain using this grain size distribution. The curve will somehow look somehow like this. For example, it's comprising of clay, say this. Next the curve grows total straight line, and next we obtain a curve somehow like this. Okay, so this straight region that we obtain from here to here, this straight region, this is such curve is termed as gap graded curve. Why gap graded? Because we are considering from here, this is 0.002 to 0.06, entire region, this portion size grain is missing. Okay, that's why we are considering this as gap. Gap means what? This portion of particle is missing. So here we have this three classification. So the results are plotted in a semi-log paper with the percentage find on the arithmetic scale and the particle diameter on the log scale to obtain the grade distribution curve. So this all are the grade distribution curves that we have obtained from this diagram. Okay, on the basis of the shapes, we can classify soil as uniformly graded. As I already told you, uniformly graded means same particle size. Okay, it is also termed as poorly graded. Okay, in uniformly graded particles, remember the voids will be greater because there will be no finer fractions in order to take up or will fill in the places of the coarser portions. Okay, in well graded, it will have particle size different. So it will have different particle sizes. Here it will be same particle size. And in gap graded, some particles will be missing. Okay, few of the particles will be missing in this case. Now, there are certain terms by seeing at the values of which we can classify whether the soil is well graded or poorly graded or gap graded. Okay, so these two terms you need to remember. The first term is the uniformity coefficient and the second is the coefficient of curvature. So uniformity coefficient is D60 by D10 and the coefficient of curvature is D30 square by D60 into D10. Now what are these things? D60, D10, D30 and all this. So when we are plotting this curve, say we obtain a curve somehow like this. When we are plotting in the y-axis the percentage finer and the x-axis the size. Okay, here we are comprising the size and this is the percentage finer. Right? For example, for say 60% finer, this will intersect somehow and will obtain a certain value. This value is termed as D60. So this is the grain diameter corresponding to 60% finer on the grain size distribution curve. Similarly, D10 will be somewhere like this. 10 for this will obtain a value. This will be D10, the dia of the particle. Next for D30 it will be somewhere like this. This will be D30. Okay, so D60 is this, D10 is the correspondingly 10% finer and D30 is corresponding to 30% finer on the grain size distribution curve. Often the question is asked which size or which diameter is considered as the effective grain size. Remember, Alan Hazen was a scientist who told with his experiment that D10 will be considered as the effective grain size. So remember these things. The D10 is considered as the effective grain size. Okay. Next, let us look at the values which we will obtain and we can classify the soil accordingly. So if you obtain the Cu, and I already told Cu is D60 divided by D10. Say if we obtain the value as 6, now what we'll consider the soil as? So it's if it's less than 5 and if it's having values very close to 1, we consider that soil as uniform size particles or we can say poorly graded soil. If it's having values 5 to 15, we consider soil as medium graded and from greater than 15, we consider it as well graded soil. So for the value of 6, what will be the type of soil? You can comment in the below section, okay? Next, if the Cc value, we know what is the Cc value? It's D30 square divided by D60 into D10, right? If we obtain this value as somehow 2, what will be the type of soil? Okay, here it's written soil is considered well graded if the Cc value lies between 1 and 3. Remember this value. So these two questions, do comment in the below section and I'll check whether you're getting things right or wrong. Okay. Next, looking at the next portion, here I have given an example or we can say it's a question, it's a problem where it's saying there's a 500 gram of dry soil is used for sieve analysis. The mass of soil that is written on each sieve has been given below. Okay, and it has been asked to plot a grain size distribution curve and determine the uniformity coefficient and coefficient of curvature. So from the uniformity coefficient and coefficient of curvature value, we can easily say whether the soil is well graded or uniformly graded. Fine. So what it has been provided is, we have been provided the sieve size. Remember, the sieve size and the diameter of the grain is similar. So if you write the sieve size, if you're getting the sieve size as 2, this will also be 2. If it's 1.4 mm, this will also be 1.4. If it's 1, it will also be 1 mm. If it's 500 micron, this will be 0.5. If it's 250, it will be 0.25. For 125, it will be 0.125, and for 75 micron, it will be 0.05. I've represented all in mm, right? This is the mass retained in gram, which has been given in the question. Next, what we need to find out is the percentage of mass retained. I already told for 10, it will be how much? 10 divided by total mass that has been taken. Total mass that is taken is how much? It's 500 grams, right? So what we'll get is 10 divided by 500 into 100. So what we are getting is 2%, right? So we write it over 2. For the next portion, this is for number 1. Next we'll do is 18 divided by 500 into 100. This will somehow will obtain it as 3.6%. So put the values of 3.6. Correspondingly, if you do for the others, you will get values as 12%, next you will get as 27%, next is 29%, 11.2%, and the last one will obtain is as 9%. Once you get this percentage retained on each sieve, you need to find out the cumulative percentage retained. I already showed you that it is the total percentage amount of salt which could not pass the particular sieve. So for the first case, we'll get that this value will only be written. For the second case, what we'll do, we'll plus 2 plus 3.6, we'll sum it up, and what we will get is as 5.6. Next again we'll sum up 5.6 plus 12, so we'll get it as 17.6. For the next portion we'll sum up 17.6 plus 27, and we will get this thing as 44.6. Now 44.6 plus of 29, this will give me 73.6, and 73.6 plus 11.2 will obtain is at as 84.8, and 84.8 plus of 9, this will get as 93.8. So this is how we can find out the cumulative percentage written. Once we get these values, we need to find out the percentage finder, because the graph in the graph percentage finder will be plotted in the y-axis, right, in the arithmetic scale, and this will be plotted in the dia of the size, or we can say the sieve size, in the x-axis, right? So this has to be found out. So what we do is we subtract 2 from 100, which will obtain as 98%. Next 100 minus all these values will do. So 100 minus 5.6 will give me 94.4%. 100 minus 17.6 will give me 82.4%. Next 100 minus 44.6 will give me 55.4%. 100 minus 73.6 will give me 26.4%, and 100 minus 84.8 will be 15.2%, and 100 minus 93.8 will be 6.2%. So what we'll do is just plot a graph in your similar graph paper. This will be your homework. Do it at home, okay? So just plot a graph. Here you need to type the sieve size in mm, right, or the particle size diameter, whatever you say, and here it will be the percentage finder, right? So percentage finder, the first one is 98%, let it be here, 94.4 somehow here, 82.8, 55, 26, 15.2, sorry, 15.2 and 6.2. So plot the graph, see how you obtain the graph as, maybe somehow you'll obtain the graph as somehow like this. Just verify what is the graph you're obtaining. I cannot plot it over here because I don't have a similar graph paper. You can buy a similar graph paper at your home and plot it. Okay, I cannot show you, but here what we get is to obtain this U value, you need this 60. So the correspondingly particle to 60%, just you plot this 60%, sorry, it will be 60%. So corresponding to these values, find out what will be D60, and correspondingly to D10 value, you find out what will be the value of D10. Okay, so let it be 10% finer. So you'll obtain somehow this graph as D10. So you'll get somehow value you will obtain from here will somehow be and say x, and if this value lies from the chart, you find out if it's less than 5 or 5 to 15 or greater than 15, and classify the soil correspondingly. Find out the cc value also, which will be d30 square divided by d60 into d10. Find out this value also, let it be y. Find out whether its y is lying between 1 and 3. If it's lying between 1 and 3, it will be a well graded soil. Fine. I hope it's clear to you this portion. In my next video, I'll come up with the consistency of soil. Till then, do study these portions, try out the sums from different books. If you have any problem, comment in the below section or you can mail me. Thank you for listening and have a very happy New Year 2020. Thank you.